all of PCC's Gmail services are down today. I don't know if anybody noticed that. It's awful. All right. So, not yesterday, Monday, we left off talking about solid solutions. We'll go back a little bit just to make sure you understand the context. So we were talking about the different group 4 materials and what affected their band gap. So remember, band gap is the gap between the conduction band, or the valence band, and the conduction band. So the valence band is down here. This, for group 4 materials, is full of electrons. All right, so electrons everywhere. This is the conduction band. For group 4 materials, it is empty. These are generally all bonding MOs. These are all anti-bonding MOs. Again, for group 4. For any other material, this is changed. This is more complicated. We're just going to focus on group 4. So this is a band gap. And the size of this band gap determines whether something is conductive or not. If there is 0 band gap, it's going to be conductive, or very little. If it's a small band gap, it's going to be a semi-metal. If it's a large band gap, it's going to be an insulator, or non-metal. Okay? And so you can see here are different band gaps. Anything above 3 electron volts is an insulator. So diamond is very much an insulator. But silicon, germanium are pretty much semi-metals, semiconductors, and tin there is a metal, a conductor. So we looked at how the size of the unit cell, these are all diamond crystal structure or zinc blend, depending on if it's a compound or not. And here is the energy of the photon that is emitted when an electron drops from the conduction band back to the valence band. So the bigger the band gap, the higher the energy. Remember, wavelength and energy are inversely proportional. So as your energy goes up, your wavelength goes down. It gets more in the UV region. This is ultraviolet. So you can see that when the size of the unit cell is bigger, and that comes from the atoms being bigger, your band gap shrinks. So what else do we know about the size of an atom and the size of the unit cell? That correlates to the length of your bond. So the longer your bonds, the smaller the band gap. We also know that bond length correlates to bond strength inversely. So the longer your bond, the weaker the bond is going to be. Short bonds make stronger bonds generally. So weak bonds give you a small band gap, which is what we expect. Metals have weaker bonds. Non-metals, which do covalent bonds, have much stronger bonds. So we looked at that. Then we looked at these isoelectronic solids. So these are also these are isoelectronic with group 4 materials. Here, germanium is the one we are comparing them to. So this is 3 electrons with 5 electrons, averaged out to 4. Notice the size of the unit cell is coincidentally all the same, so the bond lengths are about the same. So what causes the band gap to change in this case? Well, it's not the bond length, it's something else. We can look at these materials and think, oh, well, what's changing here definitely is the difference in electronegativity. Germanium has 0 difference in electronegativity with another germanium atom, but gallium has a small difference in electronegativity with arsenic. And as you go down here, they get to bigger and bigger differences in electronegativity, that delta En. And it seems that the larger the difference in electronegativity, the larger the band gap gets. We also know that the difference in electronegativity, another way to talk about that for a material is that material is more ionic. The larger the difference in electronegativity, the more ionic it is. Another way to say that is the more ionic character it has. Okay? And again, this is just showing that, hey, as your band gap gets bigger, your photon energy or your wavelength goes down. The photon energy increases, which makes sense. So this is where we stopped. Well, what if we want a material that emits a photon, go back one more, between 1100 and 1900. So like 1400. We want the a photon energy wavelength to be 1400 nanometers. How do we do that? How do you tune that band gap? Well, you have to have some material that has a band gap between these two numbers. And it's not like we can invent something in the periodic table that's between those two. So what we'll have to do is do something called a solid solution. You can mix silicon and germanium together. They're both group 4. And you can mix them in any ratio. That's what we did in lab 1 when we made alloys. And you can do any ratio you want, 20%, 80%, any number. And so generically you can write it as a formula like that. Whatever x fraction you have for silicon, your fraction of germanium is going to be 1 minus x, where x is some decimal, some fraction. So this is kind of a visual of what your solid solution might look like, going from pure silicon all the way to pure germanium, and these are just mixtures of varying amounts of silicon and germanium. And it's not like an ionic compound. So ionic compounds, you must have 1-to-1, sodium to chloride, for instance. And we did the crystal structures today. They are very well organized. The sodium and the chlorides, so the chlorides are all FCC, the sodiums are all the octahedral holes. We saw that. This is different. This is, you don't have to have that perfect 1-to-1 ratio. That's not what the formula requires. So they can be anywhere, the silicons and germaniums. They're well mixed. It's not like one side is germanium and one side is silicon. They're mixed. But it doesn't have to be a perfect crystalline mixture kind of thing. This is still crystalline. This is still going to make diamond crystal structure. It's just that the position, like what atoms they're going to be there, are kind of random. So not only can you make a mixture between two elements from group 4, you can make a mixture that includes isoelectronic materials too. So gallium arsenide is isoelectronic with anything from group 4. But why do I have just gallium and arsenic? I could do gallium and phosphorus. I could do gallium and nitrogen. These are all isoelectronic. And here's the thing. These materials are what we use to make LEDs. And the band gap that you get from these materials is what the color of the LED is going to look like. So gallium nitride has a band gap that is a specific energy that when you calculate, well, what wavelength photon is emitted, it's going to be a blue photon. Gallium phosphide has a smaller band gap, and that energy is exactly what would give you a green photon. And then gallium arsenide has an even smaller band gap that gives you a red photon. But again, what if I don't want green, red, and yellow? What if I want red and blue? What if I want a yellow or orange or a turquoise LED? Yeah, what's up?
Would a smaller band gap not require more energy to break and have the blue?
So the smaller the band gap, the less energy that the electron has to release when it drops back down.
Okay.
So small energy means large wavelength. So red is longer wavelength, lower energy, yeah. So if I want any other color, I'd have to do something called a solid solution. I could make a material that is half gallium and then half one of these, but why pick one? Why not mix them together? I could have a little bit of arsenic, a little bit of phosphorus as my other half. And that would give me somewhere between the red and the green. It would be somewhere yellowish orange, depending on the mixtures I make. So for instance, I could make something like this, gallium with phosphorus and arsenic. And these ratios are important, right? So you need to have 1-to-1, group 3 and group 5, so that you have, on average, 4 valence electrons. That's the rule. So this is 1, right? There's a 1 in front of here. We don't write 1 in formulas. These add up to 1, 0.4 and 0.6. And it works because these are both group 5 elements. And so we have that right perfect ratio of 1-to-1, group 3 to group 5, and that averages to 4 valence electrons. If you want to do it mathematically, this is the way to do it. you are averaging over 2 atoms, 1 gallium, which provides 3 valence electrons, 0.4 phosphorus, which provides 5 valence electrons, and 0.6 arsenic, which provides 5 valence electrons. And this should give you 4 if everything's right. We're going to go over this. So the generic formula, just like we did for germanium and silicon, in this case, okay, 1 gallium with X amount of phosphorus, 1 minus X amount of arsenic would give you the right ratio. If you change this ratio where it's not even amounts, then you're not going to have a group 4 material anymore. It's not going to be diamond crystal structure. It might be a semiconductor still, but it's not going to be the one that we're going to study. It's not going to work the way we expect it to work. So let's go over questions 46 through 53 on the workbook. It's in 24C. And it's not page 60, it's probably page 55. What was it? 54, okay. Thank you. Uh, 46 to 53, page 54.
I was thinking of them like bond lengths, but they're sort of the opposite. It's a longer bond, or the weaker, is weaker, but it's.
Well, when you go to nitrogen, which is smaller, yeah, the bond length gets shorter, and that will affect the band gap. Yeah, the shorter the bond, the stronger the bond, and the stronger the bond, the larger the band gap is. Yeah.
Okay.
So the more nitrogen you mix in, the more. So you say nitrogen. So between phosphorus and arsenic, the more phosphorus you have, since phosphorus is smaller, the bigger the band gap. The more arsenic it is, the smaller.
But so a larger band gap is a stronger bond and a shorter bond.
Yes, yes,
Okay.
yes, exactly. Mm-hmm. I mean, we're talking many, many bonds, so you have to look at all of them. Yeah. Well,
My kind of confusing myself.
so you can, I mean, it's just like this, where the x is a fraction. It's going to be some decimal. But it's going to look kind of like that, where there's just 1 and x involved. So.
Okay.
So, I think people who wanted to try have had a chance to wrap their head around this. I mean, it's not super complicated, but it's a different way of thinking about formula now. We're no longer limited to, hey, there has to be this many because it's a charge and all this stuff. We're kind of doing some unusual stuff here. So this formula, if you think about it, it's still talking about 2 atoms, or at least if you count the atoms. There's 1 gallium, and there is 0.4 of this phosphorus, 0.6 of this arsenic. That adds up to 1. So there's 2 total atoms. Only one of them has 3 valence electrons. Gallium has 3 valence electrons. So 1 out of 2. Right? Half of the atoms in that formula have 3 valence electrons. The other half have 5 valence electrons. Now that half is split up between phosphorus and arsenic, but they represent half of the total atoms in that formula. So both phosphorus and arsenic contribute 5 valence electrons. If you had 1 mole of this stuff, how many moles of gallium would you have?
Half a mole.
Half a mole. Actually, no, wait. Sorry. If I had 1 mole of gallium of this formula, then I would have 1 mole of gallium. So yeah, I psyched myself out. Yeah, so if I have 1 mole of this as a formula unit kind of thing, then I have like I break this apart, I will have 1 mole of gallium. So for every one of these, I will have 1 gallium, basically. So it's a weird way to think, but yeah. 1 mole of gallium. How many moles of phosphorus would you have, though?
4.
Yeah, so this is, 0.4 only. And, what is it, 9, arsenic, 0.6. And what is the general formula for the series of solid solutions made? Anybody have one?
Is it just gallium 2PAS?
So you kind of want to write it like this, where so we're varying the amount of phosphorus and arsenic, but keeping gallium 1. So keep gallium 1. I'm not going to put anything in front. There's 1 in front of there implied. But for phosphorus, I'm going to put an X in front. And if phosphorus is X, then arsenic has to be 1 minus X. So phosphorus is 0.2, gallium has to be 0.8. They have to add up to 1. So that's kind of what I would put. So phosphorus is X, arsenic is going to be 1 minus X. Okay, so that's kind of how to think about solid solutions. Now, what about them? Like, how do we gauge their properties? Well, let's start with looking at the extremes: gallium arsenide versus gallium phosphide, which has a larger unit cell. Yeah, the gallium arsenide, because arsenic is a bigger atom than phosphorus. And so it's going to make a bigger unit cell. 52, which compound would be more ionic as a result? GAP. Why GAP?
Because phosphorus is more ionic than arsenic.
Did you say more electronegative?
Phosphorus Yes, I know.
Okay, yeah.
No, I don't.
Yeah, it's more electronegative than arsenic, and so there's a bigger difference in electronegativity with gallium and phosphorus than gallium and arsenic. So, we've seen these properties already. We saw them as we went in the last section. So what is this? This is unit cell size, and this is ionic character. So when we rank, well, what if we make mixtures? So here we've got pure gallium phosphorus. This is 0 arsenic. Here we've got, and we don't have any pure gallium phosphide, but or gallium arsenide, but we have mixtures where we have a little bit of phosphorus and a lot of arsenic, and then we add more phosphorus, less arsenic, more phosphorus, less arsenic, pure phosphorus. Well, gallium and phosphorus only. So how would we rank the unit cell length? Well, we just said anything with arsenic is going to be bigger. So the more arsenic we have, the bigger the unit cell is going to be. So this is going to be the biggest. That's going to be next smallest. That's going to be next smallest. This is going to be the smallest because it's just gallium and phosphorus. Okay. Now, let's kind of take this information and apply it to what does it mean about the band gap now? Because that's the point, is how do we understand, well, what are these materials going to do to the band gap? What are these materials going to do for our photons that are emitted, you know, when these things relax? So let's try 54 to 62. And like this is the big takeaway for at least solid solutions. And they get 15 minutes for this one, so this is a lot. Let's see. You guys just want to work together on the board?
Yeah.
I feel like you guys are like worn out from the quiz, but okay. I guess you all said lab today.
It was the Legos.
Yeah. Okay, so let's just do it together. So, 54. Consider the series of monatomic solids shown from group 4 elements. We've got a series of bond dissociation energies, and we need to fill them in. So, we're looking at group 4. Here the unit cell gets bigger. The band gap gets smaller. Bond dissociation energy. This is the energy required to break the bond. So which one's going to have the largest bond dissociation energy? Diamond, right? Carbon is going to have the strongest bond out of all these for reasons. Why? How can we tell, I should say?
Because it's negatively.
It's the smallest. So smaller atoms make stronger bonds on average, okay? More electronegative is probably, well, that's probably partly true too. But we're just going to go by size at this point. So it's going to have the highest energy required to dissociate, to break that bond. So 346. And then tin is going to have the weakest energy. We already know metals have weak bonds, and that's because they tend to be larger atoms. And it is the largest. So 146 down here, and then you fill in the rest as in order, okay? So as the size of the atoms, the band gap also, the size of the atoms increases, the band gap energy also increases. True or false? Size of the atoms increases. Band gap does not increase, it decreases, so that's false. Okay, so that's group 4, regular group 4. So let's now look at solid solution stuff. Not solid solution, isoelectronic stuff. So here we've got difference in electronegativity values. So here we've got 0. Hopefully you can see immediately that one's going to be 0 because germanium compared to another germanium, no difference in electronegativity. Copper, bromine, that's going to have the biggest difference in electronegativity. You got something further to the left in the periodic table paired up with something much further to the right. And that's going to have the highest difference in electronegativity. So 0, 0.4, 0.8, 0.9. somehow, well, here it is. Two students are disagreeing about the factor in this series that affects the band gap energy. One student argues that band gap varies with size. The other student argues that band gap varies with difference in electronegativity. Here is a graph of band gap versus difference in electronegativity. Oh, no, it's actually a blank axis, x-axis. But let's kind of settle the argument. So what they're graphing here is difference in electronegativity on the x-axis. That's what's not labeled. This is basically the data from this table here. So they're graphing band gap versus the stuff that we filled in. And hopefully you can clearly see that as the difference in electronegativity goes up, the band gap goes up. We get a nice linear relationship here. So the students arguing about band gap, what affects band gap, they're actually both right? So the larger your cell, we saw that with the regular group 4 elements, the larger your cell, the smaller the band gap. So the longer the bond, the smaller the band gap. But also, the bigger the difference in electronegativity, the larger the band gap as well. Okay, so both of them affect band gap. So for a solid solution, the band gap energy for a solid solution will do what as the bonds between the atoms become more ionic? So if I make something more ionic, what happens to the band gap energy in a solid solution?
Make more what? Make it more what?
Make it more, sorry?
What did you say? Make it more what?
Ionic.
Okay.
If it's more, if the bonds in my solid solution, the mixture of arsenic and phosphorus with gallium, if those become more ionic, what happens in the band gap?
Smaller.
So remember, the more ionic something is, the bigger the difference in electronegativity. And we just saw that as the difference in electronegativity gets bigger, the band gap increases. So the more ionic something is, the larger the band gap is going to be. I wish there's not a good one here. Hold on. What are the numbers? We'll get to them. So let's start with solid solutions. This is a very good test question, 59. Actually, they're all pretty good, but this one's really good. Which of these is not a valid formula for a solid solution? So the idea is we are trying to make group 4 isoelectronic materials. So the amount of each element has to add up to, on average, 4 valence electrons. All right, so let's see how this works. The way I like to do it is, just let me copy one down first. Gallium X, aluminum 1 minus X, arsenic. What I like to do is kind of just write down what group they came from. How many valence electrons does each one contribute? So gallium is from group 3. I'm not going to put plus 3. I'm going to say it provides 3 valence electrons. Aluminum is also from group 3. It provides 3 valence electrons. Arsenic is from group 5. It provides 5 valence electrons. So remember, in my formula, I need to have 1 total atom of group 3, 1 total atom of group 5. And this should work, because just put something into X if you want. Put 0.5 if you want. If X is 0.5, then I'll get gallium 0.5, aluminum 1 minus X is 0.5, and then arsenic is 1. Well, this adds up to 1. 1 atom that has 3 valence electrons, 1 atom that has 5 valence electrons. This works. This is isoelectronic with group 4. This is a valid solid solution. I just made up something for X, just to have real numbers to work with. Not everybody likes algebra. So gallium with phosphorus and arsenic, that one. Colors again. Gallium with phosphorus and arsenic. So again, this is a group 3 valence electrons. Phosphorus is a group 5 valence electrons. This is a group 5 valence electrons. So on average, I need to have 4. So one atom of group 3, one total atom of group 4. This works as well. All right, I can plug something in for X and get some numbers just like I did up here. This adds up to 4 valence electrons on average as well. Let's try C. C is indium and aluminum and phosphorus. So indium is group 3. Aluminum is group 3. Phosphorus is group 5. So there's a problem here. Again, I have to have one atom of group 3, one atom of group 5 total. I already have one atom of group 3. There's no X in front. There's a 1 in front of here. So if I make X anything, like other than 0, if I make it 0.2, for instance. All right, so if I have aluminum 0.2, phosphorus becomes 0.8. And suddenly I have 1.2 atoms of group 3 and 0.8 atoms of group 5. That does not average out to 4. So this one's no good. This is not a valid solid solution. Okay? D is a really gnarly one, but that's not too difficult to do. Just break it apart into pieces like I've been doing. Aluminum, X, gallium, 1 minus X, in parentheses, 0.5, and indium, 0.5, with phosphorus. So, what does this make? What does this all mean? So aluminum is a group 3, gallium is also a group 3, indium is group 3, phosphorus is group 5. So the rule is one atom of group 3, one atom of group 5. I've got the one atom of group 5, that's perfect. These are both group 3. These will add up to a whole, okay? So if X is 0.3, this becomes 0.7. That adds up to 1. But in parentheses, it's half. And a half of a group 3 and a half of a group 3 adds up to 1 full atom. This works. It's a little gnarly looking, but this works. There's 1 atom total of group 3, 1 atom total of group 5. This averages out to 4 valence electrons. It's okay. See, the only one that doesn't work is C. Okay. So 60. Let's make an LED. And we're not getting into the specifics of the electronics of the LED. It's more complicated than this class needs to worry about. But the material that's used to make the LED are these materials that we're talking about. So we want to make one that is orange in color. And one impractical way to tune an LED to make it a different color, to change its color, is to change its temperature. And we'll actually do this in the lab. So if you stick an LED into a cup of liquid nitrogen and cool it down to super low temperatures, what do you think might happen to the atoms? Would they get further apart or closer together? Closer. So atoms are constantly vibrating in place. That's how they store heat energy. If you take away that heat, they will stop vibrating as much. They will get closer together because they're not kind of vibrating enough to keep everything apart. So they'll get closer together. What happens to the band gap when these bond lengths get smaller? It gets bigger. So when bond lengths get smaller, band gaps get bigger. The overlap from orbitals is better, so band gaps get bigger. So will that yellow LED change? Sorry, will that orange LED change to yellow or red if I put it in a liquid nitrogen? Yes. Yes. So the band gap is going to get bigger, which means that the photon wavelength is going to get smaller. The energy of the photon increases, so the wavelength gets smaller. And yellow is a shorter wavelength than orange. So it goes Roy G. Biv. Red is the longest wavelength, the lowest energy. So orange will slowly change to yellow. You'll see this actually. You'll see it actually go from, I think we start with a yellow one, and it'll go all the way to like blue. It's kind of crazy. Yeah.
I'm thinking of it as the gap gets higher, the height of the wave gets higher. Is that a way to think of it?
So the height of the wave, that's amplitude,
Yes.
and that only affects brightness.
Oh, cool.
Which is not, that actually is part of the lab. We're not gonna worry about it for our exam, but, no, as the band gap increases, so in an LED, you have to apply power to LEDs, right? So we're artificially exciting electrons. We're putting electrons into the conduction band, and those electrons are dropping back down to the valence band, and when they do, they emit the light that we see. So if we make that band gap bigger, then those electrons are dropping further and emitting a higher energy photon, which is going to be a lower wavelength. Yeah, because it's higher energy. Okay. So that's not a very practical way to tune an LED, although you could do it. A better way is to change the composition. So here's kind of what I was looking for earlier. If I compare gallium phosphide to gallium nitride, would I say that gallium phosphide is less or more ionic than gallium nitride?
Less.
Yeah, less. So the bigger the difference in electronegativity, the more ionic it is. So gallium phosphide has a smaller difference in electronegativity. It is less ionic. Gallium phosphide compared to gallium nitride, the gallium phosphide bonds are longer because of size. Phosphorus is bigger. And if one of these LEDs is green, the other is blue, which one is the blue one?
The gallium phos.
Would be the shorter one.
That's one explanation, yeah. So the shorter the bond, the bigger the band gap. Bigger the band gap, the more blue it's going to be. So remember here, let's actually add this to the board too. So this is low energy, long wavelength. And then we've got high energy, short wavelength. So if the band gap gets bigger, you're going to go to a photon that is more on this side. So between green and blue, blue is a higher energy photon, and so it would make sense for gallium nitride, which has both the shorter bonds and more ionic, meaning bigger difference in electronegativity. Both of those contribute to the fact that they will have a larger band gap. So gallium nitride is the blue one. It has a larger band gap.
I have a quick question.
Yeah, sorry, yeah.
So when the band gap gets smaller, is it because the bands are getting larger, or are they just moving closer together?
They're getting closer together.
Okay.
So remember that the valence band is mostly bonding MOs. The conduction band is anti-bonding MOs, and the splitting between the bonding and anti-bonding MOs is proportional to how much overlap the orbitals have. The more overlap the orbitals have, the better the bond, basically, the bigger the splitting is going to be.
So what's the relationship between the band gap and the bond length? Or is there no relationship?
So yeah, the larger the bond length,
Uh-huh.
the smaller the band gap.
Okay.
Because large bond length means bad overlap of orbitals. Short bond length usually means really good overlap, so high band gap. Okay, so now let's talk about really tuning. So gallium arsenide, gallium phosphide, each make their own kind of LED. One is green, the other is red. Gallium arsenide is red, gallium phosphide is green. Let's say I wanted to make LEDs with colors between them. Below is a graph that compares the formula for a solid solution made of gallium phosphide gallium and phosphorus and arsenic, and the band gaps for these various compositions. Okay, so we have A, B, C, and D, 4 different compositions. So let's determine the formula and color of the LED produced from this data. So here we go. So what we have here is a graph on the x-axis that tells you what the x is in this generic formula. So when x is 0, what does that mean? No phosphorus, all arsenic. If I put a 0 here, arsenic is 1. So this is pure gallium arsenide. And over here is 1, x is 1, this is pure gallium phosphide. So I've got D here is pure gallium phosphide. This is not one of our things, but this is pure gallium arsenide. Yes. And this is mixtures in between. So right here, 50-50, half-half gallium phosphorus and arsenic. And these are the wavelengths of the, well, see, these are the band gaps of these various things. And these are the wavelengths from those band gaps. So notice we can create, no, I think that's something else. Anyway, this is the data. I think if we have this band gap, this is the wavelength you get. I think this is just a table for quick reference. So the idea here is let's calculate what the, what are we calculating? This is a mess. For each composition, determine the formula and the color of the LED produced. Okay, so let's do A first. Just to give you an idea how this works. So solution A, that's this one, is 0.2 for x. So the formula is going to be gallium 0.2. That's what x is. Plug it right in. And then arsenic is going to be 1 minus 0.2, which is 0.8. That's the formula. What is the color going to be?
Red.
This is 1.7-ish. I guess it's that one, 1.77. So the band gap is 1.77 electron volts, which corresponds to a 700 nanometer photon. Red. So that's the color of the LED that I'd make that has this solid solution. If I go to B, this is right in the middle, 50-50, so 0.5. Gallium phosphorus is 0.5, arsenic is 0.5. The band gap for this thing looks to be about around 2, something like that.
Let's say like 210.
I think this one might be,
Alright.
that one might be 210. Yeah, I think this one's exactly 2. And that corresponds to 620 for your wavelength. These are listed, but you can calculate these yourself. Remember, you can convert electron volts to joules, and then plug them into your energy of a photon equation and calculate the wavelength yourself. So this is an orange one. And so, you know, we're taking these LED materials that make one color only. Gallium arsenide makes one color, gallium phosphide makes a different color, and we're generating a series of LEDs of colors in between. So that's basically how you do that one. I'm not going to do the other two. I think this is not that difficult. I guess that's it. Let's calculate one just for fun, just to make sure everybody knows how to do it. So let's do the third one. We'll calculate the wavelength instead of looking it up. But C is 0.8 for X. So it's gallium with phosphorus is 0.8 and arsenic is 0.2. The band gap is going to be around 2.15, 2.14. So let's quickly calculate that just to make sure you've seen this. First, convert this to joules. And I don't remember the conversion myself, so I need to cheat. Here we go. 1.6 times 10 to the minus 19. So 1 electron volt is 1.6 times 10 to the minus 19 joules. 3.42 times 10 to the minus 19 joules. And then I'm going to use the equation for energy of a photon. This is from 221. Planck's constant times the speed of light over the wavelength. But I'm going to rearrange things. I'm going to solve for wavelength, so it's hc over energy. If you want me to show you the algebra, I can show you to after class, but that's how you do it. So Planck's constant 6.626 times 10 to the minus 34 joule seconds. Speed of light, I'm not going to have much room here, 3.0 times 10 to the 8 meters per second. And that's all over the energy of that photon, 3.42 times 10 to the minus 19. The wavelength is going to be, I need these as constants stored somewhere, so I just push a button and keep doing this all the time. So that divided by 3.42 divided by 10 to the 19. Now, I get mistakes here. Hold on. 3.42 10 minus 19. Yeah. So I get 5.8 times 10 to the minus 7 meters after everything cancels, which in nanometers is 580 nanometers. So 580, I believe, is greenish yellow. I think it's yellowish, actually. I think it's too high, still too high for green. So it's a yellow LED. And yeah, 580 yellow. So I got exactly what they said. Make sure you know how to do that. Now let's think about why we get these colors. Okay, we haven't talked about that yet. So notice that with gallium, which has a lot of arsenic and a little bit of phosphorus, arsenic is bigger. All right, bigger atoms make bigger unit cells, longer bonds, and longer bonds translate to smaller band gaps. And so notice the band gap is 1.7. Okay? As we start swapping the larger arsenic for the smaller phosphorus, so the ratio is changing, we're having more phosphorus now, we're getting more smaller atoms, and so there's going to be better bonds, shorter bonds, more overlap. The band gap is going to start to go up, and it does. And as we keep swapping more of the small arsenic for the larger phosphorus, we get a higher band gap. You can use size, or you can also use difference in electronegativity. We're swapping something with a low electronegativity with a higher electronegativity. Phosphorus is a little bit higher. And so the difference in electronegativity between them is also increasing. It's becoming more ionic. So this is less ionic, that is more ionic, and that's why the band gap's going up. So, keep that in mind, all right, when you're thinking about what affects band gap. There's a couple things. So sometimes you can look at both. Sometimes you can only look at one thing at a time. So it should make sense. Anyway, the homework should make sense. Please try the homework this weekend. We can talk about it on Monday and make sure it's clear. All right. Any questions about this stuff so far? You guys are done.
I think I have a question actually.
Yeah.
It's not that, it's just, that's what
Trying to think about like the color that is it because I guess the atoms absorb the bigger, it's kind of hard to say. So like the lower the band gap, that means they're absorbing the smaller, or is that too kind of?
Well, okay, so this stuff, the band gap would look like that. You have a band gap of 1.77 electron volts. So the way an LED would work is you would hook it up to an electrical circuit. The electricity itself is the way of supplying energy to it, and that would promote an electron from down here to up here. And then eventually the electron relaxes, goes back down, and when it drops back down, it emits the photon with the energy that corresponds to that gap. This thing has a larger gap. So you're still using electricity to promote the electron to the higher, to the conduction band. But now when it drops back down, it's got farther to go when it drops. And it has to release that much energy, and so it's going to be a higher energy.
That makes
photon.
more sense now.
Okay.
Thank you.
All right, so just to review, metals, 0 band gap approximately. It can have a little bit, but hardly anything. Semiconductors, less than 3 electron volts. Anything else above 3 electron volts is an insulator, is not conductive. You might think, well, what if I tried to make it conductive and I applied tons of energy to it? Well, before it becomes conductive, other things will happen. It'll break down and to react with the air. It'll do weird stuff. Giving something a ton of energy is not good sometimes. It's very violent. So there is another picture of how the band gap changes based on the orbital overlap. Carbon, because it can make a shorter bond, the orbitals overlap a lot better, and so the difference between the bonding MOs and the anti-bonding MOs is a big difference. They split a lot. That's why the band gap is large. Something like 10, which is a much bigger atom, the orbitals cannot overlap as much, and so the splitting between the bonding MOs and anti-bonding MOs is much smaller. In fact, it's almost non-existent, and so you get a conductive species. Okay. All right. So, I mean, we can talk a little bit also about how conductive something might become, and to talk about that, I kind of need to introduce something called kinetic theory, which we're going to come back to later again. But focus on the blue curve, and what this blue curve here represents is if you take a sample of atoms, of anything, a metal, and you measure the energy that each atom has. Not every atom has exactly the same energy, okay? It doesn't work like that. There's a distribution of energy. Some atoms have a lot of energy, some atoms have a little bit of energy. The way you should think about it is, you know, when you play pool and you have your ball set up, you hit it with the white ball, they all go flying, but some of them are going fast, some of them are going slow, right? You're providing energy with that initial strike, and that's what happens with atoms too. When you give a material some energy, some of the atoms take a lot of energy, some of them take a little. There's a distribution of energy. And that's what this curve represents. What this curve represents is the fraction of, in this case, electrons that have the right energy to get bumped up to the conduction band, okay? So if you just kind of poll and look at, okay, well, how much energy do all these atoms or electrons have? Some of them, a very small number of them, have a tiny bit of energy, and as you go to higher energy, there's a ton of them that have this much energy. There's not many that have this much energy. So this is like the distribution of energies. The trick, and then, so this dotted line here is the average energy. You might be thinking, well, why is it kind of to the right of the peak? Why is it not on the peak? These curves are not parabolic. They're not symmetrical. They don't go up and down perfectly. They go up, and then they kind of trail off a little bit to infinity. So the average is a little bit to the right of the peak. That's why these lines are there. Okay, so that's what that is. And if you heat up, so temperature, let me go back. Temperature is a physics person is going to hate me for saying this, but temperature is, in chemistry, we like to think of temperature as a measure of the average amount of kinetic energy. Okay, that's kind of what temperature is. And like I said, if you talk to somebody who's in physics and is studying this, that's not what temperature is at all, but this is a good way to think about it. So temperature is an average amount of kinetic energy. So a low temperature substance will have, on average, a lower amount of kinetic energy. A high temperature, something that has a high temperature will have a high amount of kinetic energy on average. So this blue curve shows a material that is at 0 degrees C, and you can see that most of their atoms have this energy. On average, it's this, and the peak is kind of narrow, relatively. As I increase the temperature of my substance, what happens to the average? Well, the average shifts to the right, which makes sense. The average energy goes up, but the peak actually broadens out too. It's not as narrow. And that's what will happen with this energy distribution. As I increase the temperature more and more and more, this average will shift over and over and over, but then the peak will flatten out, it will broaden out. This is very recognizable distribution. We'll eventually call it the Boltzmann distribution, but we'll come back to that. So that's what the distribution of energy inside a material is like. So if I tell you that, okay, that we have this distribution of energies in a material, this particular energy right here is the band gap energy for that material. Well, then you can ask, well, okay, well, what proportion of atoms in that material have at least that energy or more? So what do they need that? Well, if they have that energy, then they can promote their electrons in the conduction band and they'll be conductive. If they don't have that energy, if they're below here, then that atom will not be able to put its electron in the conduction band. It will stay in the valence band down here, and it won't be conductive. So if you have a material in blue, these atoms here have enough energy to cause their electrons to be conductive. And notice there's not much. Most of the area under the curve is over here. There's a tiny fraction that is under the curve that is above this energy. But if I heat my material up, now the peak shifts to the right. This line is the same energy. The band gap doesn't change. But now look at the proportion of atoms under the red curve. There's a lot bigger proportion of atoms that have the right energy to be conductive now. So the idea here is, if I take a semiconductor, it's going to be slightly conductive. I think our conductivity tester showed that. But the higher temperature I heat it, the more atoms will have the right amount of energy to make their electrons conductive, and the more conductive it'll be in general. So that's what this is kind of trying to show you. So here, this is what happens with a semiconductor at room temperature. There is a band gap. Only a small fraction of the atoms have the right energy to push their electrons up to the conduction band. So this is not very conductive. So you can measure it, but it's not very good. So I already answered this. So how will the conductivity of semiconductors change with increasing temperature? Well, it turns out, yeah, the higher the temperature, the higher the conductivity is going to get. All right. So here's an insulator. And insulators are going to have the same kind of distribution of kinetic energy as any other materials. So the atoms inside an insulator are moving or vibrating, whatever they're doing, they have energy. And if I heat up an insulator, that distribution will shift to the right. It's just the same as the other stuff. But the difference here is that the band gap is way over here for an insulator. It's much, much higher energy. And if you were to try to measure, well, what fraction of atoms in an insulator have enough energy to push their electrons up to the conduction band, practically zero. And that's why they're insulators.
So could you make a diamond? You couldn't make a diamond conductive?
So if you gave a diamond enough energy
Yeah.
to get up there, it would burn in air, it would melt first. You just couldn't give it enough energy in solid form to do that. Maybe there's exotic materials. Maybe you could do it under super high pressures and do some crazy stuff. But that's like exotic, materials. That's not normal. Water. If you pressurize water at enough pressure, you can cause the hydrogens. So you can cause water to become a solid and a liquid at the same time. So like you can cause the oxygens to be frozen as a solid, but then the hydrogens to become loose and liquid-like. So it's weird. So yeah, in extreme conditions, you can do really crazy stuff. So yeah, yes, you'd have to do this in some kind of extreme condition to make an insulator conductive, and doesn't really work. Okay. So yeah, so with semiconductors, there's a little bit few atoms that can, or a few electrons that can get up there, and the hotter you make it, the better it is. But insulators won't. Okay. I don't know if it's worth talking about it. Let me just introduce the next topic, which is not going to be the exam, but I just wanted you to see what we're getting into. We're going to start talking about intermolecular forces. And these are going to come in, these are tied into our section by thinking about, well, what happens with graphite? So we looked at graphite, it makes layers. The atoms within a layer are covalently bonded, but how are the layers held together? There's not really a bond that we normally think of as a bond that holds them together. So those are intermolecular forces. In fact, intermolecular forces are like one of the most important forces in biological applications. So this is like this is an enzyme, and an enzyme is just a special type of protein that does chemistry. It does chemical reactions inside. This squiggly, curly stuff, this represents a long chain of amino acids bonded together. And the way that they kind of coil on each other and kind of stick together is represented by these animations, these cartoons. And we're not going to talk about that. But the fact that these things fold and make these weird shapes, really, if you unfold it, it's just one long strand. That's it. The covalent bonds that make this protein is just one long strand. So this is all folded up into some kind of shape. And the reason it folds up is because of intermolecular forces, these other forces that are not bonds that cause atoms to attract other atoms. DNA, the backbone is all covalent bonds, and the base pairs are tied to the backbone using covalent bonds. But how do the two helices bind together? So like, there's two strands, right? Hydrogen bonds, which are a type of intermolecular force. So these base pairs, if you've taken any bio, Alice talked to the adenine and thymine go together, guanine and cytosine go together. Why do they go together? They don't bond together, they interact using intermolecular forces, and that's what keeps the DNA zipped up into two helices. Okay. It's also how RNA works when the various types of RNA do their thing to express proteins from DNA. Very complicated, more than I know. So we're going to talk about that, and in order to talk about that, we're going to learn a lot more organic chemistry. So we're going to start off, and if you're welcome to learn about this while we're down. We're going to have all of next week down because we're going to do review, and then we're going to do an exam. So we're not going to do anything new for like 2 weeks almost. But we're going to talk about functional groups. We're going to talk about different kinds of compounds. So we're going to get into organic chemistry before we can talk about intermolecular forces. So feel free to like go into all that. Okay?
So Monday we're doing a review. Wednesday
is our exam only. And then we don't have a lab next week.
Yeah.
So we come to class at 1.
Yeah, so just, don't show up in the morning. Unless you want to, I mean, I'll be here, so if you want to go over some stuff, that's fine.
There's not even work, there's no work stuff, huh? There's no lab at all?
No.
Okay, so my
No.
physics class has that same thing. We're just doing a lab still. My physics class, we're doing other stuff, but it's the same time as this class.
Oh, I see, okay.
He's like, oh,
Yes.
there's a lab.
So review, and then exam, and that's it next week, okay? I need to adjust the homework, because I'm going to take this off of the homework. This is currently still set to do for written homework. I might have to adjust the master chemistry too, but there's still 24C to do. That's definitely something you should do. If you started the master in chemistry and you get to IMF stuff, you can ignore it for now. I'll fix that too, okay? All right. Have a good weekend. We're going to end early. Like, you guys don't want to learn this, relearn it again.
Question about the food. So I guess if the volume of the sphere was on there, I'm pretty sure to the density, it's just you get to decide and keep it.
That's one, yeah.
But I also was like, oh, or you take the atoms. and
So,
you take atoms.
if you were talking, so you don't want the volume of the atoms because the density is how much space the whole crystal is. The volume of the spheres is necessary when we're doing calculations for compactness,
Okay.
which we're not doing. Yeah.
So what I ended up doing, I did it the wrong way first. It took like more work, and then I
Yeah.
did it the easy way, which was right. And then I saw that they were different, and I was like, oh, so that's how much space. That's like one way of finding out how much space is in between. Because I got the sort
Okay.
of in a way.
Okay.
The volume of I got the volume of the atoms, and then the volume of the whole.
Yeah, I think you ended up, yeah.
Thing. This is from earlier. I will.
Okay,
today.
that's fine, thank you. And,
But I get it now. It
Good.
is the simple. It's just the cube.
yes, yeah, once you have the solid.
Yeah, I did NH4C.
No,
I
thank
have
you.
a question.
Yeah.
Where can I access the slides? Is there like a place?
Yeah, they're, if you go to D2L, and if you go to, I think important docs, the lecture slides right there.
Because I've been taking pictures of them.
Oh, I'm sorry, yeah, you can, they're all available, so you can do whatever you want.
Okay, and then I have another question.
Mm-hmm.
So I'm confused between covalent bonds and molecular because I thought they were the same thing, but they're not. Because
They are. When we talk about a molecular compound, that is a compound that is made with covalent bonds because you're talking about a small molecule. So like, methane is a molecular compound. It's made with covalent bonds. I guess it's not exactly the right thing to say if you say molecular bonds because it's either covalent or ionic or metallic.
So why, like in the lab, there's like a separation between like the different compounds and like then it's covalent. It's like a group.
Yeah, so there's for the last lab, so there's covalent
Yeah.
networks.
Let me get the sheet because I'm not confused.
Okay.
Just a quick question.
Uh-huh.
So what's exactly due on Monday?
I think for now is just 24C. I have to remove the
Okay.
25 C part, or 25
Because
C.
when I saw the announcement, it said it was due May 2nd, like all of it. So I was a little confused. It's like,
maybe I messed up a date or something. Okay.
Okay.
Let me double check that date. It was for the written homework stuff?
Yes.
Okay. I'll double check it, but the 24C section of homework, that you should do
Monday.
for Monday, yeah, because
Yes.
it's going to be on the exam, so you should do it now.
Yes. So I was just like, that doesn't sound right.
Sorry about that, yeah.
Yeah, no worries. Thank you so much. Thank you.
Okay. Okay, so these are different kinds of solids, first of all. And if your solid is molecular, meaning it is made up of small molecules. So for instance, you can have a solid made out of CO2, right? And that looks like that. But the solid will be this, but just in crystal form. So you have a whole bunch of these in a FCC unit cell. And that would be a molecular solid because it's made of molecules, of individual molecules.
Oh, okay.
And so there's the polar and nonpolar. So that one is nonpolar because it's a nonpolar molecule. And
yeah,
a polar
because
one
you
would be.
have to have two of the dots in the top of
Yeah.
to make it like this.
Well, it has to be bent, yeah. So
Yeah.
water would be a molecular
Okay,
polar.
yeah.
And you can make ice, that's a solid.
Okay.
A covalent network is something that doesn't make individual molecules. It makes never-ending, like diamond.
Oh, like
Which-
or like organic compounds that they have all like a lot of carbons in them. Is that what
Well,
it is?
so those are so like plastics or
Okay.
long, like the one I just showed, the long carbon chain.
Mm.
That's still a molecule. So
Okay.
a covalent network is where the bonds never end almost.
Okay.
Like so a diamond is just a whole bunch of carbon bonds that just never end. Graphite is the same way. Quartz is the same way. That is made up of, yeah, it is. It's made up of silicon and oxygen. But it just keeps going.
Okay.
But they are covalent bonds, but they don't make small molecules. They don't make things we could call a molecule. Let's put it that way.
Okay, I think I got it now.
Yeah.
Yeah, molecular is like, it's just like small molecules and then they form like. a
And you
structure.
can still make a solid out of them. Yes.
Okay, okay.
Yeah.
Thank you.